Today we will be discussing friction and circular motion. First, let's talk about friction. As you are aware, whenever a body is resting on a surface, normal reaction is the contact force between them. So the normal reaction of the surface on this body is a contact force between them. In addition to normal reaction, there is another contact force, that is friction. So whenever two surfaces are in contact, there are two types of contact forces: normal reaction, which acts normal to the surface, and friction, which acts parallel to the contact surface. Now let's complete the rectangle formed by these two. Let's complete the rectangle formed by friction and normal reaction. In this, as you can see, this is the resultant. This is the resultant of friction and normal reaction. And this is one angle theta. Theta is called angle of friction. Now, tan theta, as you can see from the figure, is F by N. This is called coefficient of friction. So let's understand clearly that the contact force is friction along the surface, normal reaction normal to the surface. Resultant of them is this one, I have called it R. Theta is the angle of friction, tan theta is called coefficient of friction. The symbol for coefficient of friction is mu, which you have already seen previously in some other contexts. For example, when you were in class 9 and 10, refractive index used to be denoted by mu. So tan theta, that is F by N, is called coefficient of friction. Now the thing is, coefficient of friction can be of two types. To understand that, let us consider one example. Let's say that there is a block resting on a surface and somebody has applied a 30 Newton force to this block, but the block did not move because of this force. Now there doesn't seem to be any other force horizontally, which means that friction on the block has to be equal and opposite to 30 Newton. So friction will be 30 Newton acting opposite to this force of 30 Newton. Now let's say this person increases the force to 70 Newton and still the block does not move, the block is still at rest. This means that now the friction force has become 70 Newton. So friction is acting opposite to 70 Newton and it is equal in magnitude. That is why the block is stationary. When the applied force is increased to 100 Newton, then also the block does not move, which means the friction value must be 100 Newton in the opposite direction. However, it was found that when you increase the force beyond 100 Newton, any value more than 100 Newton, the block starts moving. Say for example, when the force was increased to, let's say, 101 Newton, the block was found to move. In fact, any value greater than 100 Newton, the block was found to move. And one more thing, it was found that once the block started moving, the value of friction decreased slightly below this value, and subsequently the value of friction remained constant, which means even if you increase the force to 102, the friction value remains 99 Newton. Now, what are the things we learned from this experiment? First of all, we have learned one thing, that friction is a self-adjusting force. If you increase the applied force, friction will increase proportionately, ensuring that the body stays at rest. The second thing that we learn is that friction has a limiting value. So in this case, 100 Newton is called limiting friction. So this is an important thing, that there is a limiting value to the friction. Friction cannot increase beyond a limit. So in this particular context, the limiting friction value is 100 Newton. And another thing we find, that friction in all cases appears to oppose relative motion. The manner in which friction is acting, it is trying to oppose relative motion between this block and this surface. However, it cannot increase beyond its limiting value, and if the applied force crosses the limiting friction value, then friction will relent and motion will start. And once motion starts, the friction value becomes a constant, which is slightly lesser than the limiting value, and it stays constant. So this tells us that the rest inertia seems to be a stronger inertia than inertia of motion. Once the body has started moving, the body has inertia of motion, and the friction value is slightly lesser than the limiting value. When the body was not moving at all, it had inertia of rest, which is why the friction could go up to the limiting value of 100 Newton. Now, if you consider that the normal reaction in this limiting case is N, then the ratio of limiting friction, you could also call it the maximum friction, to N is called mu S. You know that mu is coefficient of friction, so this is called coefficient of static friction. So I was telling you that coefficient of friction can be of two types. So one of them is pertaining to the limiting case. So at limiting friction, the ratio of friction to normal reaction is called coefficient of static friction. Once the motion starts, in any scenario, if you find out the ratio of friction to normal reaction, so in our context it will be 99 by N, that is called coefficient of kinetic friction. So coefficient of kinetic friction is applicable for two bodies which are in relative motion, and coefficient of static friction is the maximum friction coefficient obtainable between the two surfaces, and it occurs when the situation is that of limiting friction. In fact, if we draw a graph, the graph will look somewhat like this. This is the limiting value, This is the constant value when the motion starts. So basically on the y-axis we have friction, and on the x-axis we have applied force. So as you increase the applied force, the friction value increases proportionately. That's what we saw. When the applied force is 30, friction is 30. When the applied force is 70, friction is 70. When the applied force is 100, friction is 100. So as we increase the applied force, friction increases proportionately. It achieves a limiting value, which is described in this diagram. After that, any further increase in applied force causes relative motion, and then friction achieves a constant value which is slightly less than the limiting value. So this is the basic concept of friction and how it adjusts itself, what is its limiting value, and why coefficient of friction becomes constant once the motion starts, because it is having inertia of motion, and therefore the value of friction becomes constant. Now, one important thing you must remember, that normal reaction is basically an internal force. What I mean to say is that when a block is resting on a surface, then N is the action of block on surface, as you can see, and this N is what we call normal reaction of surface on block. So N is the action of block on surface, and this N is the normal reaction of surface on block. Similarly, friction also acts in an action-reaction pair. So the surface which is having this block on top of it will give friction to this block, and the block will also give an equal and opposite force to the surface. So friction also is an internal force, and therefore friction also acts in an action-reaction pair. Now, what are the factors on which friction depends? Well, essentially friction depends on the nature of the two contact surfaces. So it depends on the nature of two surfaces. Now, if you keep two particular surfaces and if you try to polish them, make them smooth, etc., then you may be able to change the coefficient of friction. Otherwise, for a given set of two surfaces, the friction coefficient will be a constant, and it does not depend on area of contact. So it's not that if you have a larger area of contact, then you will have a greater amount of friction. It's not like that. So friction coefficient depends on the nature of the two surfaces, but it does not depend on the contact area between those two surfaces. How does friction act on an inclined plane? Suppose you have a block resting on an inclined plane and the normal reaction is N. Let's say the angle over here is theta. Now the thing is, the weight of this block, suppose it is mg. So mg will have two components, mg cos theta and mg sin theta. Mg cos theta will act normal to the contact surface and mg sin theta will act parallel to the contact surface. Now the thing is that if there is no motion perpendicular to the contact surface, then we can say that N will be equal to mg cos theta. Now what happens is that the friction coefficient is mu, so you know that mu is equal to friction by normal reaction, so friction will be mu into mg cos theta. So between this block and this surface, the friction force will be mu into mg cos theta. Now if this block is going to go down due to gravity, then friction will act in this way. But in another situation, suppose some external force is being provided on this block, due to which this block tends to go up the plane, then friction will act downwards. Now this is very important, that the direction of friction will always in every case be such that it opposes the relative motion. So this is the third thing you have to remember, that it always opposes relative motion. So this is one thing about friction, that it always opposes relative motion. So if this is the diagram, the block is trying to slide down due to gravity, then friction will act this way. But if this is the diagram, some external force is being provided on this block, then the friction will act this way, because it will try to stop the relative motion. So in both cases, the value of the friction force will be mu into mg cos theta. If there is no relative motion between the block and the surface, then the limiting friction will be mu s into mg cos theta. If there is a relative motion, then kinetic friction will be mu k into mg cos theta. So this is the details about friction and in what direction it acts. Now in motion in a plane chapter, we concluded the chapter by discussing about centripetal force. Now one thing is that in any circular motion, suppose the angle at the center is theta. Mind you, we are measuring theta in radians. So if the angle at the center is theta, and if this arc length is r, if this arc length is s, then s is equal to r theta is the relation between the arc length and the radius. So s is the arc length, is radius into theta. Now if you differentiate both sides, you will get ds by dt is equal to r into d theta by dt. ds by dt is linear velocity, d theta by dt is angular velocity. So we are having one relation s equal to r theta, another relation v is equal to r omega. Now if you differentiate both sides again, then dv by dt is linear acceleration and d omega by dt is angular acceleration. So these are the three relations between linear and angular: s equal to r theta, v equal to r omega, a equal to r alpha. Now in uniform circular motion, you know that the speed of the body is constant, so it has got only centripetal acceleration, and we discussed in motion in a plane chapter that the centripetal acceleration is v square by r. Now v is equal to r omega, so we can say that centripetal acceleration is omega square into r. So if it is uniform circular motion, then centripetal acceleration will be omega square into r. Now suppose that it is not uniform circular motion, the speed is not constant. In that case, what will happen? The rate of change of the speed, it will be equal to the linear acceleration, or you could say the tangential acceleration. So in a circular motion which is non-uniform, apart from radial, centripetal we can call it radial, we will also have tangential acceleration. So the resultant acceleration will be due to both of them. So the resultant acceleration will be the resultant of v square by r and dv by dt. One important thing about centripetal force is that whenever you have any circular motion, if we consider the motion of the earth around the sun as circular motion, any circular motion must necessarily have a centripetal force. So if we consider the motion of the earth around the sun, it is an orbital motion. We could approximate it to a circular motion. Because it's an orbital motion, there has to be a centripetal force, and that centripetal force is provided by gravity of the sun. So the gravitational force of the sun is the centripetal force. So when the earth is orbiting the sun, the gravitational force of the sun is the centripetal force. Now suppose there is a road with a circular turning. Suppose there is a road with a circular turning, and let us say that there is a vehicle, and for simplicity let us consider that this vehicle is traveling with a constant speed v. Because the vehicle is having a constant speed v and it is a circular turning, there has to be a centripetal force, and that is obviously mv square by r. But I told you that centripetal force has to be provided by something. In this case, centripetal force is provided by the gravitational force of the sun. So who is providing the centripetal force in this case? It is the friction between the roads and the tires. So in this case, it is the friction between the roads and the tires that is providing the centripetal force. Now you know that friction has a limiting value. Friction cannot be unlimited, it has a limiting value, and you know how the limiting friction is calculated. It is coefficient of static friction into normal reaction. Now the thing is, mv square by r is being provided by friction, but friction has a limiting value. So you could say that mv square by r should be lesser than equal to the limiting value of friction. I'll repeat this again. You know that friction between the road and the tire is providing the centripetal force, but friction has a limiting value, that is mu s into normal reaction. So mv square by r should be lesser than the limiting value of friction. If you write normal reaction as mg, then you will get v is less than equal to mu s into rg. So the speed of this vehicle has to be lesser than equal to mu s into rg. Now let's understand this physically. Physically, what does it mean? Physically, it means that whatever the speed at which the driver is driving the car, the friction between the tire and the road is able to give the car the centripetal force which it needs to make a circular turn. But if the speed of the car is too high, then friction will not be able to provide the necessary centripetal force for this car to complete a circular turn, which basically means that the car will skid out of the road. So for a safe turn, the speed of the car should be lesser than equal to mu s into rg. So you can say that this is the safe limit for a circular turn. But there is a situation which is very extraordinary in this context. What if the same thing was happening on a hilly terrain? Then how will we analyze the situation? Suppose that a vehicle is on a hilly terrain, and because the terrain is hilly and there has to be more factors of safety apart from safe speed limit, etc. So what the road designers do is that to enhance the safety criteria, they raise the road by an angle theta. This angle theta is called banking angle. So for extra safety, the roads are inclined at an angle theta with respect to the horizontal. Theta is known as banking angle. Now suppose this is the vehicle. Now for this vehicle, let us say normal reaction is as usual, it is n, weight of the vehicle is mg. Now the thing is, this vehicle is making a circular turn. Now you have to remember the situation is very similar to what we discussed earlier, except that this is a hilly terrain. So if the vehicle is going too fast, it may skid out of the road. So friction will try to oppose that. So friction will act in this way. Now let us resolve the normal reaction into two components. As you can see, if this angle is theta, then this will also be theta. So this is n cos theta and this is n sin theta. These are the two components of the normal reaction. Similarly, let us resolve the friction into two components. This angle is theta. So this is f cos theta and this is f sin theta. So looking at the curvature of the road, it is fair to say that n sin theta and f cos theta together will provide the centripetal force. So we can say that the centripetal force mv square by r will be equal to n sin theta plus f cos theta. Also considering vertical equilibrium, mg plus f sin theta will be equal to n cos theta. If you consider the vertical equilibrium, mg plus f sin theta equal to n cos theta. Now suppose we divide these two equations. This is what we will get: n sin theta plus f cos theta by n cos theta minus f sin theta is equal to mv square by r mg, which is basically v square by rg. So if you divide these two equations, you will get n sin theta plus f cos theta by n cos theta minus f sin theta equal to mv square by rmg, that is basically equal to v square by rg. Now you know that the friction is capable of adjusting itself till it reaches the maximum value. So if you put friction equal to the maximum value, that is mu s into n cos theta, that you put in the numerator, and in the denominator also you put mu s into n. Just replace friction with mu s into n above and below. In that case, you will get this relation and all the n's will adjust itself. So the safe limit for speed, it will be equal to this. So once again, when you have a plain circular road, then the speed limit is given by v is less than equal to mu s into rg. But when you have a hilly terrain, then for extra safety the road should be inclined with respect to the horizontal or banked with respect to the horizontal, and in that case the centripetal force is n sin theta plus mu s into n cos theta. And when we equate that to this mv square by r, and then we equate the vertical forces and divide them, for the maximum speed limit we can replace friction with mu s into normal reaction. So the maximum speed limit is given by this. So this is the topic, friction in circular turnings and friction in banking of roads. Now we come to a very important topic, that is centrifugal force. Let's say that there is a very large heavy drum and it is capable of revolving about its axis, and it has a heavy box on the floor, and the box is being viewed by two people, one on the ground and one who is inside the drum. So basically the situation is like this, that both the people are looking at the same object but with a different point of view. One person is outside the drum, one person is inside the drum. Now when this person is asked to comment on the forces that are acting on the drum, he says that there is friction between the floor and the box, and this friction is providing the centripetal force. So according to this person who is on the ground, he says that this box is performing circular motion as a result of the revolutions of this drum, and the centripetal force required for the circular motion is provided by friction. So he says that friction is equal to mv square by r. Now when you consider this person, remember that he is a part of the same motion as the box. So for this person, the box will be stationary because he and the box are a part of the same motion. So since this person's frame is non-inertial, you will have to apply a pseudo force which is equal and opposite to the centripetal force, that is mv square by r, and friction between the box and the floor will act towards the center, and due to these two forces being equal and opposite, the box will be in equilibrium. So when you discuss this box from the point of view of the person on the ground, we describe this box by saying friction equal to mv square by r. But when you discuss this box from the point of view of person inside the drum, we say that the box is in equilibrium because friction and pseudo force are acting equal and opposite. This pseudo force is called centrifugal force. So I'll tell you the exact definition of centrifugal force, you can note it down. Centrifugal force is the pseudo force which is applied in case of circular motion when the observer himself is a part of the motion. For example, here the observer is a part of the circular motion, so his frame is non-inertial. I have told you in laws of motion that if the observer's frame is non-inertial, you will have to apply a pseudo force, and this pseudo force results in this block being in equilibrium. So you can now understand that centripetal force is a real force which is manifested as gravitation or as friction, whereas centrifugal force is a fictitious force which is only applied when the frame of reference of the observer is non-inertial, as it is in this particular case. Now let us discuss a situation where we can apply centrifugal force. Suppose there is a body on the surface of the earth, and the line joining the body to the center of the earth makes an angle theta with the earth's axis. Incidentally, theta is called the co-latitude. Suppose this point is P, so theta is called the co-latitude of the point P. Now this body, it will have a force which will attract it to the center of the earth. That force we call the weight of the body, so that is equal to mg. Now this body is also rotating. Thanks to the rotation of the earth, this body is also rotating, and you can see that the radius of its orbit is equal to this distance small r. So small r is the perpendicular distance from this body to the axis of the earth's rotation. Let us say capital R is the actual radius of the earth. So the person who is observing the motion of the body is also a part of the earth's rotation. So a pseudo force has to be applied, which we now know is called centrifugal force. So a centrifugal force has to be applied to make the frame of that observer inertial. Once again I repeat, the person who is observing the motion of this block is himself a part of the earth's rotation. So a pseudo force m omega square small r will have to be applied to make the frame inertial. Now once you apply the pseudo force, you will have to take the resultant of mg and m omega square r. A very good way of doing that is, if you consider that this angle is theta, so this is also theta, and the component of m omega square r in this direction is m omega square small r into cos 90 minus theta. I repeat, m omega square into small r is the centrifugal force, and the component of centrifugal force in this direction is m omega square small r into cos 90 minus theta. So the resultant force on this block, suppose we call it as mg dash, it will be mg minus m omega square small r into cos 90 minus theta. So that is mg into m omega square. Now look at this diagram carefully. You will see that small r is nothing but capital R sine theta. So instead of small r you write capital R sine theta, and instead of cos 90 minus theta you write sine theta. So we are getting g dash equal to g minus omega square into capital R sine square theta. Now when you are at the equator, then at the equator theta equal to 90 degree. So g dash equal to g minus omega square r. and when you are at the poles, theta equal to 0 degree, so g dash equal to g. So you know this is a very famous result, that acceleration due to gravity is minimum at the equator and maximum at the poles. And now you can see why that is happening, because at the equator acceleration due to gravity is g minus omega square r, whereas at the poles acceleration due to gravity is g dash equal to g. So this is a very important application of centrifugal force, which shows us what is the effect of the Earth's rotation on acceleration due to gravity. So with this we complete the chapter friction and circular motion.